Hello Math 119 and 119X students. So for this video we're going to learn about what is the meaning of the level of confidence, and also we'll learn about the assumptions, what would happen if you violate the assumptions when you do a confidence interval for the mean. So we're going to do a simulation of some confidence intervals for a mean, and if you watch this before we cover section 8.2, in 8.2 we learn about the t-interval. So we're going to be doing t-intervals. We're going to have a small sample size of 10. The population mean will be known, it'll be 50, and our standard deviation will be 10. Okay, so let's simulate some confidence intervals. So here we have 100 simulated confidence intervals, and we have a normal, first of all, we have a normally distributed population with a mean of 50. So we have a small sample size, but we have a normally distributed population. So when you do a confidence interval, there's two assumptions you have. One is that your data come from a simple random sample, and the second is to satisfy the central limit theorem, you have the assumption that your data come from a population that is normally distributed, or you have a large sample size, which is greater than or equal to 30. So in this case, we satisfy the assumptions because we have a small sample size, but we have a normally distributed population. So we satisfy that assumption. And so we generated 100 confidence intervals where our level of confidence is 95%. And notice that, first of all, we have some green lines and some red lines. Okay, each of these green lines or red lines is a simulated confidence interval. The little dot is the mean. So actually you can put this on a like this one here. You can see that this is, I think, the fourth one from the top. The simulated mean is 45.466. Our lower limit simulated, our lower confidence interval, our lower t-interval limit is 36.218, and our upper limit is 54.714. Well, the population mean is 50, so this confidence interval contains the true value of the mean, right? Because the true value of the mean is in between the lower limit and the upper limit. So all these simulated intervals that are green, they all contain the true value of the mean. So you can see some of them are a little bit longer and some of them are a little bit shorter than the others. That tells us that the margin of errors are not all the same for each one. Like the short ones have a small margin of error, and the longer ones, like this one's a fairly long one right here, has a fairly large margin of error. This one is a short one, it has a fairly small margin of error. So the margin of errors vary depending on the sample. So the green ones all contain the true value, all contain 50, which is the true value of the population mean. But some of them don't contain 50, like this red one here. With this red one, the simulated mean is 58.642, the lower limit is 52.654, and the upper limit is 64.629. So this red one here does not contain the true value of the mean. So that means if you actually calculated a confidence interval like this, it would be completely inaccurate. This confidence interval does not contain the true value of the mean, so it's a completely inaccurate interval. So how many of the intervals contain the true value of the mean and how many of them don't? Well, 96 contain the true value of the mean. There's 96 green ones and there's 4 red ones. So that's 96%. Well, our level of confidence is 95%. So we would actually, it's close to what we would expect. We would expect 95 out of 100 to contain the true value of the mean, but we actually got 96. So let's do this a few more times, because you can see that if we simulate another 100, the results won't come out the same, most likely. They'll come out a little bit different. So this one, we actually also got 4 red ones. Let's do 500 total. Now we got only 3 red ones in that 100. We'll do 2 more. Now we've got 400, and that one had 4 red ones. Oh, look, this one has a lot of red ones. So this one has 5, 6, 7, 8, 9, 10 red ones. So we got 90% green out of the last 100. But overall, we have 95% because we got 475 green ones out of 500. So that's 95%. So that's what we expect to get. We expect to get 95%. Okay, so what I want to do next is I want to violate one of the assumptions, and I want to stick with a small sample size, but I want to use a population that's not normal. So we're going to do this over again. So this one will do the same thing over again. Confidence intervals for a mean. So now instead of a normal distribution, I'm going to have a right skewed distribution. And we'll see how, let's just see how the results change. We'll still have a sample size of 10, and we will have a confidence level 95%. So everything else remains the same. We just have a right skewed distribution instead of a normal distribution. So now we don't satisfy the assumption. So let's see if the results still come out to be about 95%. Let's see what happens. Oh, wow, this time we only got 85% green. So let's do 500 and see what the overall rate is. See, that one we got a lot more red ones than before. Let's see what happens here. Once again, a lot more red ones than before. Right now we're at 86% green. Okay, this one we also got more than 5 red ones. We got one more. And that one's better than the others. We only got, well, we actually got 10 red ones. So our overall rate is 87%. So that's what happens. That gives you an idea of what happens when you violate one of the assumptions. You expect to have a 95% level of confidence, but our simulated level of confidence is only 87%. So that's why it's important that that you don't violate the assumption. You either want a normally distributed population or a large sample size. Okay. So actually, I'll do it one more time, and this time we'll have a right skewed population, but we'll have a large sample size, and we'll see if the results come out to be more accurate, because then we will not be violating the assumption. So let's see what happens. So we will go to confidence interval for a mean. So what I'll do is I'll just, first of all, aside from the percentages changing, if I make the sample size 30, what do you think how do you think the results will change? Do you think the green lines will be a little bit longer or a little bit shorter? Well, I would think a little bit shorter, because a larger sample size generally gives you a smaller margin of error. So our green and red lines should be a little bit shorter. So let's see what happens. Okay, so this time, even though we have a normal population, I made a mistake. Let me do it again. So confidence interval for mean. I wanted to have a skewed population. Okay, so now we have a skewed population and a large sample size. Let's see what happens. Actually, it's not much of an improvement with the larger sample size, because we got 87% that time. Let's do 100. Now we're at 90. Well, it's a slight improvement. We're at 90. Now we're at 91. Okay, so it's not really 95%, but it's still an improvement over the previous results, because we had well below 90%. This time we have 91%. So I would guess if you make a larger sample size, like 40 or 50, the results would improve. Okay, so that's what I wanted to demonstrate. And so that's it.